morning to everybody. My congratulations go to the organizing committee for having achieved such an incredible results, including us all together. I'm humbled by standing here in front of you and addressing this audience. I would start with introducing myself. I'm a transplant surgeon with an interest in kidney and pancreas, but I'm also a scientist, I'm a surgeon scientist. This is the most correct terminology. I Wake Forest. And whatever I do actually is at the intersection between transplant and regenerative medicine. So if you ask me, do you do transplant alone? I say no. Do you do then regenerative medicine alone? I say no. What I do is actually something I like to call regenerative transplantation. And the reason for which I'm emphasizing this will become clear during this presentation. So I was dragged in the field of mitochondrial transplantation almost by accident by one of my major research partners, Benedetta Bussolati, who's at the University of Turin. She's the current president of the Italian Society of Extracellular Vesicle. She's the incumbent president of the International Society of EV. She's an expert in transplant nephrology and regenerative nephrology. So in 2019, the year before COVID, she calls me and she said, listen, I have a brilliant PhD student, Andrea Rossi, who's conducting fancy research in a field called, at that time the terminology was mitochondrial transfer. And I said, okay, tell me about it. And she said, well, we're using this in a pilot in which we are using it to mitigate ischemia reperfusion injury in the kidney. And the pilot that they designed, that they were conducted, was very straightforward. So they were using immortalized cells extrapolated from the kidney, tubular cell line, that were subjected to a stress to produce damage. And some plates containing those cells were being treated with mitochondria isolated from a healthy cell line, where others were being treated just with the placebo. And those plates were being followed for 3 days, 72 hours. This slide summarizes the endpoints that they were studying: the proliferative capacity, ATP concentration. You read them. And the results were pretty neat and clear, showing beneficial effect both in terms of ATP production, cell proliferation, as well as in the ability to contain, so to mitigate the damage itself. Also, when the Krebs cycle was studied, the effect was remarkably pronounced. And also when they studied the production of oxygen radicals, they were less present in the plates that were treated with that approach. So those data was pretty interesting to us. But the question for a transplant operator like me was, is there any room in transplant for these? Do we really need mitochondrial transplantation in transplant medicine? And actually, the answer is we really do. We really need it, even badly maybe. And why is this? So I don't know how familiar you are with organ transplant, but there's a paradox. There is a nonsensical paradox that we face in transplant. Is this, that we discard the majority of the organs that we procure. That makes no sense, right? So just think about the kidney, which is the most important organ in terms of where importance is determined by the fact that it's the most transplanted. And in America, we procure a number of kidneys, but we discard 30% of them. Some of them, they are clearly non-transplantable, but the majority of those organs are transplantable. And so the question that you may ask me is, maybe, so why are you discarding that? Actually, there are no standard criteria. There's not a precise absolute measures for which we discard them. It's the fact that the average transplant surgeon, for example, when he or she receives an organ that's been out of the body for more than, for example, 12 hours, the decision that is made is, let's dump it, let's wait for a better organ, which is a tragic decision. Also, another good reason to consider this approach is this. In America, we're about to witness a revolution, more or less, something that we can call a revolution, which is the advent of this type of donation, the uncontrolled DCD donation. I'm not going to go into details. So basically, the uncontrolled DCD donor is the patient who lands at the ED dead. So whom we don't know how long the downtime has been, maybe we don't know the cause. So what we're trying to do, to make a long story short, what we need to do is to find a way to turn that individual into an organ donor. And it has been estimated that America may produce 10,000 donors a year. And to give you an idea of the impact of that figure, think about that in America last year we did almost 50,000 transplants using 17,000 deceased donors, which means that if we had another 10,000, we increased by 60% at least this pool. The problem of those donors is that the quality of the organs is in theory poor. They are considered suboptimal. And so at baseline, the average transplant surgeon would consider those 20,000 kidneys non-transplantable, so we need something to make them transplantable. One last consideration is the fact that in America we have decided that by December 31st of 2026 we need to reach the milestone of having done 60,000 transplant in the calendar year 2026. And how are we going to do that? We need to use more and more suboptimal organs. So we need to find a way to somehow make those organs better. So let's use the term repair those organs. And actually, we've been trying to develop technologies to repair organs for as long as we've been doing transplant. Actually, we have here sitting on the first row the president of ESO, the European Society of Organ Transplant, is an expert of this field, Gabriel Onesco. And this slide summarizes the different approaches that are being studied now. The one that we are talking about today is, this can be categorized as the cell by-products approach, because mitochondria are considered byproducts of cells. And there are two approaches, which is the EV approach, and again, the mitochondrial approach. So a consideration to make is that, I don't know how familiar you are with the field that is labeled as regenerative medicine. The NIH defines regenerative medicine as that field that aims to repair or replace damaged cells, tissues, and organs. So if you accept this definition, and we do accept this definition, so mitochondrial transplant is a biotechnology that should come under the umbrella of regenerative medicine. And I'm emphasizing this because the first time, Lance, you may remember, right, I had a conversation on the phone, so I met, not physically, but at least in a conversation with Lance. I brought this up and I almost shocked Lance. But we really believe that if you have interest in regenerative medicine, you should consider these technologies as part of the family. So going back to my story, and the story of my group, so after Benedict shared that data, the first thing I did was I did my homework and I searched on PubMed. Clearly the name that recurs all the time is Jim's name. Somehow this event also celebrates his pioneering work and leadership, and I called him, and you know, he's from Harvard. The Harvard guys have a very bad reputation for being unapproachable and a little arrogant. He's at the other side of the spectrum. We became buddies, like he's a buddy of each of us. And so we assembled a team, including some partners of ours at Virginia Tech, who has developed through the years cutting-edge perfusion system, and this was my team at that time. And we designed a very straightforward pilot because the interest of Benedetta in getting me involved, getting us involved, was helping her out at basically confirming the data in a clinically relevant model. And what we did, we purchased some pigs, we sacrificed the pigs, we procured the two kidneys, we merged them in a bath at room temperature to produce the damage that would mimic the damage that you would find in suboptimal kidneys. And then we treated one of the kidneys with mitochondria and in interim had been isolated from the psoas of the same, psoas is a muscle of the same animal. And then the male kidney was treated with a saline, basically. And so we put them in a perfusion system and we kept them for 24 hours. During that time, what we did, we conducted some Raman spectroscopy investigations on the solute, so in the perfusion that we collected 6 hours, 12 hours, 18 and 24 hours, and we did some basics and specialized histology, immunohistochemistry, including RNA-seq analysis. The Raman data were pretty much extraordinary. So Raman is a technology where you basically use a laser and you bombard the object that is interest for you, in this case the solution, the solution. And basically, based on the composition of that entity, you will generate a spectrum that will be representative of the molecular composition of that entity. And so, in this specific case, the more molecules you identify, the more pronounced the damage. And so what we observed was that the two groups localized at the opposite of the spectrum, which was extremely interesting. And the samples deriving from the kidneys that had not been treated actually localized at the part of the spectrum where the number of molecules was higher. So this was a direct proof of the fact that the damage was mitigated in the kidneys treated with mitochondria. Even in the case of immunohistochemistry, we could prove the beneficial effect of mitochondria, and I'm not going to spend too much time on RNA-seq. For those who are familiar with this technology, this is very much operator dependent, and what we were shown and we published on the surgery was that the treatment revealed a significant modulation of genes and pathways associated with mitochondrial metabolism. So the next step was, we reasoned this way. We thought, these are decent data. How much time do we have? 5 minutes. Decent data. Why don't we combine our experience with the Harvard experience? So we went to the FDA and they said, well, it's fine for us as long as it's fine for the IRB. We went to the IRB, they said the same. It's fine for us as long as it's fine for the FDA. And so we placed an IND, and this is the feedback that we got. When I read it, I fell off the chair. But we're working on it. We are also applying this to beta cell replacement. At this point, I'm not going to present the slides because we don't have much time, but the results are pretty promising. And I will conclude with two slides. This slide summarizes one of the slides that actually Melanie has already shown, and is telling us that there is still a lot of work to do, even if we have milestones that have been set by Jim's work. And some final remarks to make. I'm not going to go through all of them just because of the time, but it still remains uncharted territory with numerous hurdles to overcome and questions to answer. The problem is, do we really need to answer all those questions? Because as Melanie was commenting about, as long as we show efficacy, safety first and efficacy, I think that justifies the fact that we pursue on this path, and that's what transplant has experienced. Like, we've been doing transplant for 50 years. 50 years ago, we didn't know much about how the immune system works, but transplant was working extremely well, and could be considered one of the greatest milestones in the history of medicine last year. So I conclude here. Again, thank you very much to you all for being here.
Thank you so much, Dr. Orlando. And again, to open up to any questions from patients or patient representatives. Okay, anyone from the scientific community or anyone abroad has any questions, please?
My name is Hara. Also, I'm from Feinstein. So I had a previous question to Melania, but I can ask you also yeah, it was there. You can answer the question how long does it survive outside the body, the mitochondria, and how quickly you have to transfer to the other organ? Or during the a mito bank I heard, so
well,
yeah.
Gene, you want to answer that question? It's, I regularly get his experience, so I think it's the guy who should answer this question.
We isolate them and put them in within an hour. It only takes 30 minutes to isolate the red. So there's no point in leaving them around. We find they start to lose efficacy. So if we were to